Today, we'll be solving LeetCode 51, n queens. First, let's understand the goal in plain terms. We have an n by n chessboard, and we want to place n queens so that none of them can attack each other. Queens attack along rows, columns, and both diagonals. Because each queen must be safe, a clean way to reason about the puzzle is to place exactly one queen per row. That instantly removes row conflicts, and now all we need to guard against are column conflicts and diagonal conflicts. The pattern here is classic backtracking, also called depth-first search with undo. We try a choice, explore deeper, and if it fails, we undo that choice and try the next one. This is a combinatorial search and a great example of constraint checking with fast O(1) lookups. Let's map out the core idea before we code. We'll move row by row. In each row, we iterate over every column and ask, if we drop a queen here, do we collide with any existing queens column or diagonals? To answer that in constant time, we keep 3 sets, one set for used columns, one set for used main diagonals where we index by row minus column, and one set for used anti-diagonals where we index by row plus column. Those two diagonal indices work because on any main diagonal, the row minus column value is constant, and on any anti-diagonal, the row plus column value is constant. Note that row minus column can be negative, which is fine, we're just storing integers in a set. Now let's walk line by line through the solution as if we're reading the code together and talk about why each piece exists and how it works. We start by defining a function that takes n inside. We first create an empty list named results that will collect every complete, valid board. Next, we build an empty board. Think of it as a list with n rows, where each row itself is a list of n characters. We fill every cell with a dot character to represent an empty square. Then, we prepare 3 empty sets named cols, diags, and anti-diags. The cols set will contain every column index where we already placed a queen. The diag set will contain each value row minus column that is already occupied by a queen. The anti-diag set will contain each value row plus column that is already occupied by a queen. Next, we define a helper named backtrack that receives the current row we're trying to fill. First, inside backtrack, if row equals n, that means we successfully placed a queen in every row from 0 up to n-1. At that moment, we need to convert the board into the exact output format. For each row list, we join its characters into a single string, then we append the list of n strings to results. Then we return to explore other possibilities. If we haven't finished all rows yet, we loop column from 0 up to n-1. For each column, we check safety in O(1) time by asking 3 questions. Is the column already in cols? Is row minus column already in diags? Or is row plus column already in anti-diags? If any is true, this position is unsafe, so we continue to the next column. If the position is safe, then we place a queen. Concretely, we set the board at the current row and column to the letter Q. We also record this placement by adding column to cols, adding row minus column to diags, and adding row plus column to anti-diags. Then we move to the next decision by calling backtrack with row plus 1. When that recursive call returns, we must undo our move so we can try another column in the same row. This is the key backtracking step. We reset the board at the current row and column back to the dot character. We also remove column from cols, remove row minus column from diags, and remove row plus column from anti-diags. Then the loop continues to test the next column. After we define backtrack, we kick off the search by calling backtrack with 0 to start at the top row. Finally, we return results to the caller. A couple of important details to highlight. First, why use sets? Because membership checks in a set are average O(1), so every is this safe test is constant time. That makes pruning fast and keeps the code simple. Second, why row minus column and row plus column? Because they label diagonals uniquely. 2 queens share a main diagonal exactly when their row minus column matches, and they share an anti-diagonal exactly when their row plus column matches. Let's talk complexity. Each row can branch to as many as n columns, but many branches are pruned early due to our constant time safety checks. In the worst case, the search explores a number of states on the order of n factorial, since you can think of it as choosing a distinct column per row, but with pruning it is often much less. Building each saved board costs O(n) to join the rows. So the overall time is exponential, commonly described as roughly O(n factorial, dominated by the search, not by the formatting. Space complexity, ignoring the output, is O(n). We store at most n columns in the cols set, at most n diagonal values in each diagonal set, and we have a recursion depth of n. If we include the output, we also store all solutions, which is O of number of solutions times n. Before we wrap, let's identify the reusable patterns and tools you can carry to other problems. The pattern is backtracking with a state description that allows O of 1 validity checks. The tools are sets to guard constraints, a board that we mutate in place for speed, and a clean undo step after each recursive call. This exact approach extends to problems like placing bishops or rooks, generating permutations with constraints, and solving many grid-based puzzles. And that's how you solve LeetCode 51. Thank you for watching, and let's keep learning.